Hi, everyone. Thank you for joining this demo session about ARM performance solutions for heterogeneous platforms. This session follows yesterday's talk at the Embedded World Conference entitled Optimizing Heterogeneous Compute Platforms for Domain Controllers. My name is Florent, Solutions Architect at ARM, and I'm joined by two colleagues, Daniel and Martyn, who are part of our software engineering team. To avoid technical issues, we have pre-recorded the demo session, but the three of us are here live to answer any question you might have at the end. So before we start with the demo, I'd like to give an overview of where heterogeneous systems can be found, for example, in automotive. Automotive systems have greatly evolved over the last years, from vehicles with hundreds of electronic control units to a few domain controllers. You might even find one central computer for the whole car in the future. This evolution is driven in part by autonomous driving technologies that have increased the amount of sensors and the need for compute power. As a result, domain controllers are large, heterogeneous SoCs where many ARM IP can be found. They are designed to handle the various software functions of modern vehicles, advanced driver assistance systems, or in-vehicle infotainment, for example. These functions can run in different OS environments and may use different types of hardware, ARM CPU, GPU, or NPU for machine learning. To understand the performance of the whole system, tools able to tackle the diversity of environment and hardware are essential. We have illustrated some use cases during our talk yesterday, but today we will focus on software for digital cockpits and how to optimize graphics with the performance analysis tools that are part of ARM Development Studio. I'll hand over now to my colleague Daniel, who will get you through the demo session.
Hi. I'm Daniel Baines, and I'm a software engineer at ARM, and I work in the ARM Mobile Studio team. Today I'm going to be showing you Streamline and how you can profile an Android application with it. So now we're in ARM Streamline Performance Analyzer. This is a tool that allows you to profile CPU and GPU workloads. In this demo, we'll be profiling an Android application. The test scene in this application is quite simple, and it's based around the premise of car dashboards, but basically all it's doing is drawing circles. Here you can see a few screenshots of the application. Now take note of these three coloured circles, we'll get back to them later. The application is basically drawing a 1000 pixel circumference circle in the middle of a 1080p screen. Now this is a simple constant colour shader and a simple pass-through vertex shader. There is no real complexity in these shaders. This is really about how do you triangulate the circle to get the best out of the GPU. But before we look at profiling this application, I'll show you how you can capture data from the application within Streamline in the first place. So we've just opened Streamline and you're presented with this Start tab. And provided Streamline has managed to locate your copy of ADB, you can already see a list of connected devices. So this is the device I have connected to my machine right now. If it doesn't find ADB, you can always go into the preferences here and you can quickly point it to the executable. So as I mentioned, I have a device connected to my machine and you can see it listed here. I've already installed the test application on this. So it's important to make sure that you install a debuggable version of an application on the device in order to be able to capture the data from it. So once you've selected your device, the next step is to select the application you wish to profile. So in this case, the application is named com.arm.mstutorials. So we can see that it's here in the list and it's ticked to say that it's debuggable as well. Now if you wish, you can go ahead and just start the capture straight away. However, it is normally useful to configure the counters first, which you can do by pressing this button here. Now, here you can see a list of all of the hardware counters available on this device. And you're able to decide which you'd like to capture by clicking them. But the best thing to do if you're new to Streamline is to select a template by clicking this button based on the GPU on your device, which will select the appropriate counters for you. So the device I have connected is a Mali G72, so we can click this here and we can see that 84 out of the 86 counters are available and they'll automatically be added once I click this. In a future release of Streamline, we hope to automate this so that an appropriate template can be selected for you automatically. So we can save this, and we're now ready to start the capture to begin profiling the application. So if I click this, save the capture, and now we just wait for the application to start on the device. The application automatically starts on the device, and we can see the data is now coming in live. When you're ready to end the capture, you can simply press stop up here. Then you must wait a few seconds while Streamline processes this data. And there, the capture is complete. You see, it's a relatively simple process to profile Android applications within Streamline. Now I'll talk you through the profile application by switching to a capture that was taken on another device earlier. Now this demo is quite GPU focused, but before I touch on that, let's look at some of the other things Streamline offers. So we can see the CPU activity and the CPU cycles here, and if we expand these, you can look at these per core. You can also see at the bottom, we've got a heat map. We can also look at a core map. This is really useful because you can see what cores are running what, one of the things being switched between cores, and if you're pinning things to cores, you can check that's actually working. We've also got hot functions here if you include debug symbols, which can be really useful, as well as call paths. But as I mentioned before, this is quite a GPU-oriented demo, so we'll be focusing on those features of Streamline today. We have 3 schemes in the application, which we can track using these markers on the top of the capture. There's a Streamline API, which you can use in your application to add these markers programmatically to help with your profiling. So if you remember the screenshots from before, the 3 coloured circles, red, green and blue, are what we're seeing here. So the red markers indicate the triangle fan scheme. So we have a pivot vertex in the middle of the circle, and we're just rendering a fan of triangles out from there. So you get increasingly long, thin, diagonal triangles from the centre of the screen. In green, we have a triangle strip. These are long, thin triangles running vertically up and down the circle. And finally, in blue, we have the max area algorithm, which is a recursive algorithm where each iteration acquires the most area it can to build up that triangle. Ultimately, as you've seen, for these 3 cases, what ends up on the screen is pretty much identical. The vertex positioning is the same, the screen coverage is the same, but the efficiency of the GPU processing these things is very different. That is the message we're trying to get across here, that geometry matters, especially when you are doing high-resolution UIs. For example, we chose circles for this demo as it fits into the representation of dials on a car dashboard, but the same applies to rounded corners on any UI. Generally, GPUs hate long, thin diagonal triangles, so this is a way you can get much better efficiency out of your GPU. One thing to note though is that the frame rate on this device is still 60 FPS across all 3 cases. It is quite a fast GPU and it's only rendering at 1080p, although we'll be able to see that GPU does have to work faster to maintain this frame rate. This capture has been done on a Galaxy A51 5G. It's a 6-core Mali G76 with a 12 pixel per clock GPU, so quite a fast GPU. Each tick within these 3 cases is a sub-scenario, and you can see the number of triangles here is increased with each. So let's talk you through some of these counters and what they're showing us. So if we look at the Mali pixels here, we can see the pixel count is a fairly flat line throughout, and this indicates that we're hitting a comfortable 60 FPS through all the scenarios. So now let's look at the Mali GPU usage. This shows us how busy the GPU is working. In the first case, we can see that as we add more and more triangles to the GPU, it has to work harder and harder. And towards the end, this green line we see is the tiler active kicking up for the last few tests. But in most cases, the work is all fragment shading. Even though what the user sees on the screen is entirely the same, we can see how much more work the GPU is doing. This is because GPUs really don't like long, thin diagonal triangles. The middle case stays much more flat. This is long, thin triangles running vertically up and down the screen, rather than at an angle, but we still do see a kick up in tiler active towards the end. In the last scenario, we don't see any kick up in tiler active, and we can see it's much flatter all the way across. So this is suggesting that we're feeding this in a way that does not require the tiler to work anywhere near as hard, even though the triangle count is the same. And if we look at the Mali GPU utilization, this reflects the same thing really. We can see again the tiler utilization is only 4% here, where it's much higher in the other cases. The next thing to look at is the Mali memory bandwidth. So we can see for this first case, the peak bandwidth is 13 megabytes, whereas we compare that to the last case, it's only 4 megabytes. So this shows how we're making much more effective use of the GPU caches when we use the max area algorithm. Next thing I want to look at is the Mali geometry usage. This counter shows us the geometry being passed into the GPU, and it shows you how many primitives are being input, whereas how many are actually visible on screen. In the first algorithm, we can see that this is the same. Again, the same with the second. But with the third, we see towards the end here, we're actually culling quite a large amount of primitives, with less than half of them remaining visible because they're so small. And we can see this reflected in the culling rate graph below. We can see that the Mali geometry culling rate is high. And this is actually a Mali-specific culling scheme, and it tests small triangles less than a few pixels across against a rasterizer pattern and discards them early. So basically, some of those triangles in this case are so small they are redundant and they can be culled, and this really helps the GPU. Now if we look at overdraw here, this tells us the number of fragments per pixel being shaded. Now for the max area case, we can see this number doesn't really change. So that suggests that everything we're shading is actually contributing to an output pixel. But in the other cases, we can see towards the end especially, this increases, and we end up shaving over 3 times more fragments than we really need. This is because of pixel quads, where we spawn fragments as 2 by 2 pixel patches, and as we get longer and thinner triangles, what you find is that for each patch, only some of those have coverage inside the triangle, but we still use 4 slots worth of shader resource. This is also reflected in Mali core warps. So another counter that's really useful to look at is the Mali core workload property rate. Now I've already done this here, but essentially if you don't like certain counters, you can just remove them. You can even modify their expressions or add your own, or even add your own charts entirely, if you wish. So I've removed some of the less important counters in this case, so we can really focus on the partial coverage rate. Now this is a percentage of quads that are being spawned with partial coverage. So you can see, even in the first iteration of the first case, 28% of the quads being spawned here have partial coverage. By the end, every single quad spawned has partial coverage. The second case is slightly better, but in the end, we still get to 100%. See, the third case, we only have about 10%, and that stays constant. So, in summary, this is really all this demo is trying to show. Drawing triangles and how you can do comparative analysis across different algorithms. But this is really useful, and you can really already see the difference here. But there may be cases where you see things in Streamline that you don't really understand. You know, why is this higher, or you need something more visual. And this is where graphics analyzer can come in. So I'm going to hand you over to Martyn now, who's going to use this same demo and show you what graphics analyzer can do for you.
This is ARM's graphics analyzer. It's a tool that allows you to debug your graphics applications that are using APIs such as GLES or Vulkan. In this demo, we will look at the same application that Daniel has just demonstrated with Streamline. Start a new device connection by either selecting the new device connection icon in the toolbar, or by selecting Device Manager from the Debug menu. Selecting either of these will bring up the Device Manager dialog. It supports both Android and Linux IP connections, but today we are focusing on Android. As soon as the dialog is launched, it starts looking for connected devices. Here we can see the unique ID of the device connected and the name that's been retrieved from the phone. As only a single device has been detected, the Device Manager automatically starts discovering the packages that are available for debugging. Once the package list is available, you can choose the package that you wish to capture data for. The API selection section allows you to choose which APIs you would like to capture. Once we are ready to begin capturing data, we can click the Start Capture button. The GUI updates telling us the progress of installing the infrastructure needed to begin capturing data from our application. Once everything is installed, the application will be automatically launched on the device, and then data capture can commence. This view shows us the frames that have been collected. At this point, we can continue with live capture, or we can save the capture for later review. Before we start digging into the capture that we have of the application that Daniel demoed earlier, let's touch on some of the high points of the features and functionality of Graphics Analyzer. First, we'll start by loading the capture that we've taken. As the file is loading, you'll notice that we get progress information in the status bar. This helps us to know that something's going on, particularly during large file loads. The trace outline view shows all of the frames that are part of this capture. As you can see in this capture, there are a large number of frames. For this demo, we're only interested in looking at frames that also have frame buffer captures. This allows us to compare the screen contents to ensure they are as we would expect. Luckily, we can filter down to only those frames that have features enabled, one of which are frame buffer captures. We can expand each frame to show the render passes that make up each frame, and each render pass can be expanded to show all of the draws. This view provides information on the API calls themselves. For every API call that is present in the trace, we get a sequence ID, the return value of the function called, the function name, the parameter name of every parameter and its value. We can also add bookmark notes, which are useful when debugging different issues. I've already annotated this trace with a couple of bookmarks to help when I'm moving backwards and forwards through the content. In the right-hand view, we get statistics about the trace and average values of metrics for vertices and instance vertices across the different frames. In the function call tab, we get the name of the function, the names of the parameters and their values. This updates to reflect with whichever API call you have currently selected. The buffers view shows any bound buffers for the draws that you're expecting, and you can also see the contents of the buffers. The vertices view shows all of the vertices that are supplied to the draw along with their values. The uniforms show values that will be passed through to the shader, and the target state shows the current EGL and GL program state, which you can inspect and ensure is reflecting the values that you would expect. Returning to the vertice view, we can also inspect the geometry of the draw. This represents the circle that we can see in the frame buffer view. Checking the uniform view, we can see that the value, considering this is an RGBA value, is red, green, blue, alpha. As red is 1, it's fully red and there are no green or blue components. And the colour is also fully opaque, as this value is also 1. Let's just check and see what the shaders are doing, and that they are as simple as Daniel's earlier mention revealed. By going to the Assets view, we can look for the shaders under the OpenGLES section. The shaders that are currently used are shown in bold. By double-clicking, we can reveal metadata about the shader as well as their source code. Here we can see a very simple vertex shader. It simply passes the supplied input position to GL position, which makes it available further down the graphics pipeline. Shader 5 is the fragment shader, and it takes the input color supplied by the uniform, as we saw above, and sets the fragment color to that color. As this is a fully red, opaque color, we would expect to see the same in the frame buffer. And indeed we do. We've also confirmed that the shaders are as simple as Daniel suggested, and so we know that most of the work being performed in the frame now will be down to the complexity of the geometry rather than the complexity of the shaders. Looking at this view of the circle, you might wonder why the center area is black. This is because there is a large amount of triangle density in the middle. This is where all of the lines and pixels that make up the triangles are intersecting, because this area is very small and there is a large number of triangles being drawn. In this case, the triangles are made up of 576 vertices, and as you can see, they all combine at the center, providing this area of black. Let's have a look at another frame capture and see if we can notice any differences. As the bookmark shows, we're still displaying a red circle. But this time the number of vertices is 9,000. This is approximately 18 times more vertices than in the previous capture that we looked at. The huge number of triangles filling the circle explains the reason why the circle is completely black. The density of the triangles and their overlap means that everything is being overdrawn excessively, and although this makes no visual difference to the circle, as we can see if we zoom in to actual size, we are having to deal with a lot more geometry, and this geometry takes up memory and requires bandwidth to transfer between the CPU and the GPU. 18 times more than that was needed for the previous version, for no difference in output quality. Probably not a great design choice, but at least Graphics Analyzer can help us identify these issues. Let's take a look at the next frame capture. In this capture, we've changed the color of the circle, but nothing else has changed in terms of its visual appearance. The quality of the circle is identical to that of the previous red ones. We do, however, notice a big difference in the visual appearance of the geometry. This time we're drawing a circle using triangle fans. As you can see, there is no longer an area of large triangle density in the center. This has moved out to the two horizontal edges. We are using only 570 vertices to draw this circle, which is less than we've used in any of the other examples. We still get the same output, and we have a lot less areas of overlapping triangles, which means that a lot less overdrawing is taking place. This is a much more efficient way of drawing triangles to make up the circle that we're looking for. The next method of drawing triangles uses space subdivision in order to make most effective use of the number of triangles. In this example, we have 570 vertices, but most of the triangle vertices are along the circumference of the circle, where they can provide greater quality, rather than large areas of the center where they provide no benefit whatsoever. The final frame capture is with just over 1100 vertices, and you can see that the circle is identical or a little bit smoother than it was in the previous example. However, the areas of overlap are confined to the circumference of the circle, which is where you want the detail to be applied, not in the huge open area of the circle where we don't need it. For this particular use case, we are not making use of the full capabilities of Graphics Analyzer, as we are only looking at very simple shaders and simple frames, with only one render pass each and a couple of draws. However, even with those caveats, we can see that Graphics Analyzer is a very good tool for confirming what your application is doing versus what you may think it's doing. It was very good at identifying the fact that even though there was no difference in visual appearance, we were sometimes using extremely high numbers of vertices, which all goes to generate higher bandwidth and memory requirements. Using the Mobile Studio tools together, as in this example, where we reviewed a capture of an application that we initially analysed using Streamline, provides benefits that are greater than the sum of the parts. If you'd like to find out more about our tools, please visit our website. The roadmap for these tools is very exciting. We are looking into adding frame profiling via some new tool technologies, as well as adding many other useful features. Please come and talk to us. We'd love to hear your feedback and get your feature requests.
Thank you very much, Martyn and Daniel. So as Martyn mentioned, if you would like to know more about the tools that we have presented, there are two websites that you can visit. You can go to arm.com for the product pages of ARM Development Studio that includes Streamline and Graphics Analyzer that have been presented. ARM Development Studio is in fact a whole bundle for software development on ARM IP. Whether you need to develop bare metal, software, or RTOS, Android, Linux applications. For existing targets as well as future ARM IP, thanks to virtual prototypes. And in addition to the performance tools that we have presented, it also includes compilers as well as debugging tools. You can request a 30-day trial license directly from this website. For technical resources, documentation, tutorials, or videos, you can visit developer.arm.com. Specifically, you will find more information related to Streamline and Graphics Analyzer in the component section of Development Studio page. Feel free to get in touch by email or on the virtual booth to discuss, get product information. We have now about 15 minutes for questions. So please use the Q&A window to ask them. Me, Daniel, and Martyn are here to answer them live. So to initiate the conversation, let us know what particular application you would need help with. Feel free to share what type of project, application, or environment you're working on, and what are the performance challenges you're facing